Okay, so I'm actually going to start with this slide. I know we're supposed to do topic 7 notes, but I want to start with this slide because I really want to recap what you should have watched yesterday in my YouTube video. Because it was a kind of important lesson. There were a lot of really challenging concepts that hopefully you understood, but if you didn't, I want to recap them. The first one is the idea that gravity is a two-directional kind of force. We often consider gravity to literally just be, well, the gravity is pulling this apple back down. Right? If I were to draw a free body diagram of the apple, you'd say the apple is getting pulled down. And there's nothing wrong with that. But what Newton was trying to reconcile was how that fit in with his third law of motion. And Newton's third law, he stated that every force, every action force, has to have an opposite reaction force. And so if this swimmer right here pushes the wall pushes her to get her moving. Or if this swimmer pulls water backwards, the water pulls the swimmer forwards. Or if the skateboarder, where is it here? If the skateboarder pushes against the ground pushes you back. Newton was struggling to reconcile where the other force was in this concept here, because in theory there should be an opposite force of some type here, right? And this one does not make sense to people at first, because what Newton hypothesized is that the Earth itself was getting pulled up. And this makes no sense to us because we don't perceive the Earth as getting pulled up. We only really perceive in our reference frame the apple falling. But in theory, this is what is supposed to be happening, is that there should be that equal and opposite reactionary force. You know the story of Newton having the apple fall on his head? I don't know what's true and what's not. It's a legend either way. But I don't think that Newton just all of a sudden had this eureka moment going, oh, gravity exists. I think what he realized, though, is that he was getting pulled up towards the apple just as much as the apple was getting pulled towards him. Okay, so let's talk this through then. In theory, if I drop an object and it hits the ground, I've now told you that the ground came up towards the object. Why did we not see the ground move? Well, for one, we're on the ground. So if the ground came up, we came with it. But even then, even if that, Chris, that doesn't make sense. Maybe here's the best way of describing it. Remember Newton's second law, the law that says that F net equals m times a? The bigger the mass, the less the acceleration. The smaller the mass, the bigger the acceleration. You guys recall that inverse relationship? Okay, so let's say there's a force of gravity acting on this book. This book has a small mass, therefore it has the ability to accelerate because the book has a relatively small mass. But in theory, if the Earth is undergoing the exact same force of gravity, the Earth is huge. So therefore, if the Earth has a huge mass, will it accelerate a whole lot? No. So much so that its acceleration is really negligible. It's really a fraction of a percentage. But that changed things. And so here's what it allowed Newton to do. Newton was then able to figure out that there was a direct relationship, and I'm going to use this vocabulary a lot over the course of Physics 20 and 30, but he realized there was a direct relationship between a mass of an object and the force of gravity. If you use a heavier object, you get more gravity. But it wasn't just one object. He realized that there must be two masses for there to be gravity. Can you guys keep it quiet, thanks? So he realized there must be two objects for there to be gravity. There has to be the apple and the Earth, or there has to be me and the chair. There is gravitational attraction between any two objects that have mass. It's actually the foundation for how we believe the universe actually was created, is that after the Big Bang exploded everything, gravity started to clump matter together, and the clumping of matter together eventually caused the fusion that occurs in stars. But if it wasn't for gravity making all of these particles be attracted to each other, there would be no stars, because everything would just be kind of floating out in space just randomly. So, okay, there's step one. He realizes there's a direct relationship with mass. But he also realizes that there is an inverse relationship with distance. Maybe I'll use this picture as an example. We recognize that in outer space, there's really no gravity out there, right? We've seen pictures of people floating in outer space. There's no gravity. But that doesn't make sense because the Earth still has a mass. These ping pong balls or oranges, whatever they are, they still have a mass. Why are they not getting pulled downwards a certain direction? Well, it has to do with the second property. Newton discovered that there is an inverse relationship between the distance between those objects and the amount of gravity you get. And this is the way that we draw the reciprocal relationship. This is where if you make one go up, the other goes down. Any of you guys who've taken Math 20-1, you should recognize this. This is the graph of y equals 1 over x. Okay. So Newton puts all of this together, and he makes himself a formula that kind of starts with these two premises. Masses make more gravity, distances make less gravity, and he builds himself a formula, F equals m1, m2 over r squared. And then he tests it. And so he measures the masses of objects. He measures the distance between them. He measures the force of gravity. And it doesn't work. And it is frustrating. You guys have been here at some point in life, right? It should work. It's not working. And he couldn't figure it out. And what he then realized is he had to apply a constant. And this is the first constant that I'm aware of that's really been like discovered. It was the constant g. I call it big G to kind of differentiate from little g. And it was eventually discovered that this constant was 6.67 times 10 to the minus 11. In a way, this constant is kind of like, I used this with my last class. Do some of you guys know the term leading coefficient in math? Okay, if that makes sense to you, a leading coefficient in math kind of like directs how an equation kind of works a little bit. Maybe it's kind of like that, where you have to have like a number that goes in front of all the rest of your numbers. For those of you guys who don't know what I'm talking about, if I gave you the equation ax squared plus bx plus c, like you could consider this right here to maybe be like a leading coefficient. It kind of modifies the x squared value. I don't know if that makes sense at all. If not, ignore that. So, anyways, this leads to a conversation. Why do we need constants, Chris? Like, doesn't that like, shouldn't physics be able to explain things without the use of them? Well, the reason why we need constants is based on the fact that when we measure these masses in kilograms and we measure this radius in meters, it's kind of arbitrary. Like, why does a meter have to be this far? Why couldn't it have been this far or this far? Like, we just kind of randomly chose a certain value. And I think I probably told you guys this story a few times now, but like there probably still is, like the official meter stick in like a museum somewhere. And if you wanted to know what a meter was, you had to compare to that one. That was like the gold standard. Right? It's arbitrary though, isn't it? So this constant helps to kind of deal with the fact that our units are somewhat arbitrary. Why couldn't we have measured this in pounds? Why couldn't we have measured this in inches? Side story. You guys ever heard of MIT, the school MIT? There's the engineers there. I forget the name of it, but they have a unit of measurement they make their students work in called like a Kelvin or something like that. And literally there was a student that went to MIT, I think this is their story, and he was quite short. And so rather than measuring things in meters, they always measured things in Kevins or whatever the kid's name was. And so Kevin was like 4'9" or something like that, right? And so whenever they did all their calculations, they didn't measure it in meters per second squared. They measured it in Kevins per second squared, as just being silly, right? You can see a bunch of like engineering students at MIT being silly like that, right? Anyways, the point I'm trying to make with this story is that a meter is kind of arbitrary, just like an inch, just like a Kevin or whatever the kid's name was. Right? So that hopefully helps explain why many of the formulas we're going to begin to work with have constants in them, because we have to kind of correct for how we just arbitrarily made our units. Okay, long story short, Cavendish eventually did an experiment that then allowed us to calculate the force, the big G formula. He did this sort of little torsion balance experiment. I won't go over that too much in detail now, but long story short, he managed to calculate big G. And this was groundbreaking. Once we discovered that big G was 6.67 to the minus 11, that allowed us to do something called universal gravitation. And I'm now going to hop into my next set of notes, because I kind of covered what I wanted to. I'm going to hop into these ones right here and talk about why universal gravitation made a big deal. Okay. Physicists on Earth, they experimentally knew what gravity was. Okay. They knew that gravity was 9.81 because they just did this experiment a million times. They recorded the distance something was above the ground. They recorded how long it took to fall, and they knew velocity initial was 0, and they solved for acceleration. And they did experiments over and over and over, always 9.81. That's called experimental physics. I'm going to close the door here. But that's only one of the two main branches of physics. The other branch of physics you might have heard of is known as theoretical physics. Okay? Anybody watch the TV show Big Bang Theory? If you have, this will make sense. If not, sorry, I'm wasting your time. But On the Big Bang Theory TV show, there's two physicists, Leonard and Sheldon. Leonard is an experimental physicist. It's his job to make an experiment, to try to test things. Theoretical physicists spend most of their day trying to make equations. Okay. If I were to go back in my notes here and talk about experimental versus theoretical physicists, Newton, when Newton was trying to make this formula right, where's the formula? When Newton was making this formula right here, he was undergoing theoretical physics. He wasn't doing any experiments. He was just saying, this is what I think the equation should be. Right? He had good logic behind it, sound reasoning. But then when Cavendish did his experiment, that would have been experimental physics, kind of proving it. Right? Good physics really involves both. An equation that we can use and an experiment that confirms it. And it can kind of go either way. You can either start with an experiment and then try to come up with the math that fits it, or you can start with math and then try to make an experiment that fits it. But if I go back to the slide right here, this is where I want to start. Physicists had known that gravity was 9.81 for years, and they knew it because they did experimental tests. If you ever see the word empirical, empirical means experimental. So they had done tests on it. But now they were able to prove that gravity was 9.81 meters per second theoretically. And I'd like to show you how to do that. We're going to take a slide right here. If you want to follow along, you can write this down. I'm going to prove that the gravitational field strength on Earth is 9.81 meters per second, and I'm not going to do any experimental data. Okay? I'm going to use the big G formula. So I call this the big G formula, G m1 m2 over r squared. So let's just start plugging in some numbers here. G, we always know the big G value should now be 6.67 times 10 to the minus 11. Okay, let's take an object, just a random object, like say my stapler. I don't really know what the weight of my stapler is, so just for the sake of argument, this is way too big, but why don't I make it 2 kilograms? I know that's way too much, but just so you have a random object that weighs 2 kilograms. What is that random object going to be attracted to? Well, I mean, everything else in the universe that has mass, but most specifically to the Earth. And we actually know the Earth's mass now. We believe it to be 5.97 to the 24. If you watched my video yesterday, did you watch the video yesterday? No. Okay. If you watched the video yesterday, we talked about how they proved that that was the mass of the Earth. The last number we're going to need then is the distance between my stapler and the Earth, which is to the center of the Earth. So we need to know the radius of the Earth, which was 6.37 to the 6. By the way, I have them memorized because I've used them a lot. They're on your formula sheet. Did you guys catch that when you watched my video? So there's all sorts of constants on the formula sheet here. Okay. I need a calculator. So I'm going to try to calculate the force of gravity now between my 2 kilogram stapler, which is massive apparently, and the Earth. So give me a second here to type this in. Somebody help double check, would you? 667 to the minus 11 times by 2 times by 597 to the 24 divided by 637 to the 6 squared. Okay. I got a value of 19.62 basically. Anybody else try it? I know it's right. Don't worry about it. Because I can actually do the last step in my head here. This is the force of gravity according to the big G formula. However, the other way that we've learned that we can calculate the force of gravity is using the little g formula, the one that's force of gravity is mass times gravity. If this is actually indeed the force of gravity like we think it is, why don't we plug it into the little g formula and just confirm? Let's put 19.62 right here. And why don't we solve for the little g value? Let's check and make sure it actually is 9.81. Now, here's the thing. What mass do I need to put right here? Well, the mass of the object that was falling, which I just randomly said was 2. So let's put a 2 right here, times it by g. What I'm really saying is just divide both sides by 2. This is why I didn't need to have anybody confirm it, because I know if I divide that by 2, I've now solved for g as being 9.81. Now, what's cool about this is that I didn't take any measurements. I just pretended that a mass in theory, hence theoretical physicists, was 2 kilograms. And I made up some numbers and tried it out. But here's the cool thing. You know how I times by 2 up here? Eventually I was going to divide by 2 down here. It didn't matter what the mass was. This mass could have been 12 kilograms. Well, then later I would have divided by 12 kilograms. If this mass had been 712 kilograms, later I would have divided by 712 kilograms. It would not have mattered. Gravity would always work out. The math would always work out to be 9.81. And this was really validating because scientists who had just spent the last number of years testing it with an experiment now knew that they were right because they had some theory to back it up. Does that make sense? Cool. Okay, let's move on. So what we use in physics to try to describe a force like gravity, we use the word action at a distance. And I should have talked about this in my YouTube video yesterday. There are 3 forces that we know of that we call action at a distance forces. They're forces that, so there's like an attraction or a repulsion, and the 2 items don't have to be in contact. Right? If I were to throw this book, I know why it moved. It's because I physically touched the book and threw it. But if you have magnets, for example, if I put magnets this far apart, they could actually like suck in and like come towards each other, right? Same thing with gravity. Do you guys know what electrostatics means? Electrostatics refers to like positive and negative charges. And so if you have a positive charge and a negative charge, they'll attract each other. If you have like negative charges and negative charges, they repel. So there are actually 3 fields that we're going to talk about in physics. We're only going to do gravity, though, in Physics 20. We'll do electricity and magnetism in Physics 30. I'm actually doing it with my class right now. But they're all considered to be action at a distance forces, where something happens without direct contact. And one of the ways that we try to represent this, it's really simple. It's not like groundbreaking, but we draw arrows. An arrow describes what would happen. And so if you were right here, you would get attracted towards the Earth, right? And if you were over here, you would get attracted towards the Earth, right? And so we call that a field. Basically, a field is a way of kind of illustrating what's happening. But let's compare that to the moon. Does the moon have as much gravitational force of attraction as Earth does? Well, no. Why? Because it has less mass. And so you can see that not only do I have less arrows, but they're smaller, right? The size of this arrow has been much smaller compared to these big arrows, indicating that, yeah, if you were on the moon, you'd get attracted to the moon, but not that much. There's minimal gravity on the moon. If you've ever seen videos of like Neil Armstrong or Buzz Aldrin when they landed back in 1969, like they could bounce off the surface of the moon. I could dunk on the moon because there's not that much gravity, right? Like there's less force of attraction. I can't dunk regularly, so. Here's another example to kind of illustrate fields. This is actually Earth's gravitational field in a photo. And really the same thing is happening right here. You know how a field, you know how north, like how a compass points north? Okay. Imagine that like this was the North Pole up here. Well, a compass always points towards the North Pole. So if you're over here, the compass points towards the North Pole. It would point towards the North Pole. Let's say you were even flying in a space station above the ground. A compass above the Earth in a space station, the compass would actually point towards the North Pole. I mean, normally we're on the Earth itself, but in theory, that compass would still point north. So that's kind of what we do, is we draw lines pointing in certain directions, letting us know which way different things would go. So again, these arrows are all pointing in because you would get sucked towards the surface of the moon or Earth. So this leads then to our next formula. This is the last formula in our unit, and it's going to look very familiar. The formula is little g is equal to big G m over r squared. I'd like to explain where this formula came from. We now can work with universal gravitation. This was a big key. Up until now, scientists could do stuff on Earth, but now they could make predictions about gravity anywhere in the universe. And this was really instrumental for NASA. When they wanted to send astronauts to the moon or to Mars or wherever, they need to be able to predict how much gravity there's going to be. Because they need to know, is there going to be a lot of gravity? Is there going to be a little amount of gravity? And we can now calculate the gravitational field strength if you know basically 3 variables. Well, 2 variables. One is big G. That's a constant. The other one is the mass of the object. That's like the big object, like the object providing the pull. Let's call it that. If I say the object providing the pull, that would be like Earth or the moon or a comet, right? Are you or I, are we really going to create much gravitational field? No. But Neptune would. It's big enough. And then R is the distance that that planet has, basically. Okay. If I could go back for a second here, you know how this slide right here, it almost looks like the force of gravity formula? Except it's missing one of the M's. Can I point that out? Doesn't this formula look like the big FG formula? But we're missing one of the M's? Let me go back a few slides here. You know how when I did this calculation here and I solved and proved that gravity was 9.81? You know what I didn't really need to use was this randomly chosen mass. I just randomly said it was 2 kilograms, and then I changed it to 12 and to 700 and whatever number, right? But this mass right here, didn't I eventually take that number and divide by that number way down here? So if I wanted to, I could have just skipped this number entirely. And if I just skip this number entirely because I'm going to cancel it altogether, what really happens is rather than finding the force of gravity, you find what's known as the gravitational field strength. And basically what the gravitational field strength is, it's the acceleration of gravity. It's a fancy word for how much does gravity accelerate an object. On Earth, it's 9.81. But on the moon, it doesn't accelerate at 9.81. So that's what we're going to try to calculate over a couple of practice questions here. So let's pretend that we're on the moon, for example. I found some data here to help us. But let's say that we're on the surface of Earth's moon. How much does gravity actually pull? So here's how you'd solve that. You'd use our new formula. G equals big G, m over r squared. And let's find out just how much gravity actually accelerates things on the moon. Quick thought. Do you think this is going to be bigger than 9.81 or less than 9.81? Less, right? Because the moon's smaller, right? So plug in some numbers. Big G, 6.67 times 10 to the minus 11. The mass of the moon is 7.35 to the 22. And the radius of the moon itself, because you need to know how big the moon is 1.74 to the 6. And do not forget to square that number. Kids often forget the squared sign there. Okay, so I'm going to try to calculate this. I got this, 1.62. Give you a second to try typing that in just to make sure. 1.62? Okay. Now the units for this are going to be meters per second, just like they would be for the acceleration of gravity on Earth. It's just this is the acceleration of gravity on the moon. It's about a sixth as big as Earth's, give or take. If you divide 9.81 by 6, it's around this. So think of little g as a fancy word for an acceleration. It's very specific. It's the acceleration due to gravity. Just don't get into your heads that gravity is always 9.81. It's not. Sometimes gravity is something else, depending on where you are. We really only work on Earth, but this was groundbreaking. That's why I want to point out this was now universal gravitation. We can now calculate gravity anywhere, hopefully. Let me try one more. Let's try to find gravity on the surface of Jupiter. If I got to find gravity on the surface of Jupiter, it's the exact same thing. You just change out two numbers. You still go 6.67 to the minus 11. You just use Jupiter's mass. Now, Jupiter is like one of the biggest planets in our solar system. You guys have done like basic solar system stuff at some point, right? Like Jupiter has that red dot, that red spot in the middle of it. That red spot can fit like 200 or some Earths inside of it. I don't know what the number is, but like Jupiter is way bigger than Earth. So let's use Jupiter's mass. It's 1.90 times 10 to the 27, that is. Now, although Jupiter is bigger in terms of mass, it also has a bigger radius, though. Its radius looks like it's 7.15 to the 7. So all we got to do is just change out a couple of numbers here. Before you press enter on your calculator, though, should Jupiter have a bigger acceleration or a lower one than Earth then? Bigger, and probably way bigger, because Jupiter is a larger planet. So bear with me while I type this in. 7.15 to the 7 goes there. 1.90 to the 27 goes there. I got 24.8. Okay. Now, for a little context here, from what I understand, Jupiter is an uninhabitable planet for humans because what would happen is the gravity would actually crush us. Yeah, like our bones and muscles would actually get like, can you imagine like a trash compactor that like squishes you downwards? That's what would happen to us. In outer space, by the way, you guys ever heard of the phrase microgravity? My grade 9s learn about it, so I just taught it last semester. Microgravity means that there's basically very little gravity in outer space. What ends up happening is humans who go on space journeys for a while, their muscles get weaker. Their hearts kind of don't beat so strong anymore. They actually get taller. And one of the reasons why is that there's no gravity to like encourage your muscles to keep working, right? Our muscles work every day because we have to walk. But if you don't have to walk in outer space, then your muscles kind of weaken. And your blood has to get pumped to your whole body. And so your heart has to pump blood all the way down to your toes as well to your fingertips. But if there's no gravity in outer space, you don't have to pump the blood down and have it come back again. Does that make sense? Your heart has to pump so hard that it pumps all of the blood to your extremities, and it still has to have enough pressure for it to get back to your heart. Right? But if there's no gravity, then the getting back isn't going to be so hard because blood doesn't have to go uphill against gravity. Does that make sense? Long story short, your heart doesn't work as hard in outer space either. And so your muscles weaken, you get taller because you stretch out a little bit due to lack of gravity. I don't know why I got on this tangent, but anyways, outer space does weird things to people. Oh, I think I got onto this because I wanted to point out gravity on Jupiter is like uninhabitable. It's too strong. Any questions so far? We're almost done. I got 2 slides left. You're good? Okay, so let's do one more example. I want to talk about something called your weight versus your mass. Yesterday in my YouTube video, hopefully you watched it and you heard me talk about how we use these words wrong. We use the word weight often when we mean mass. Weight, well, let me start with mass. Mass is how much of something there is. We measure it in kilograms. So if I ask you how much, when you stood on the scale, what did the number say? You're really telling me a mass. But a weight in physics, a weight is always measured in newtons. And the reason why I think we use these words interchangeably, I have a scale here. I've got a demo we're going to do here. Is that when you step on a scale, what's really happening here is that this scale right here, it has a spring of some type inside of it. And as the spring gets compressed, you can see the little dial thing. It starts to move a little bit, right? So this thing goes in a circle as the spring gets pressed on. And the reason why it's doing that is normal force. I'm going to draw a bit of a picture here. Imagine that this is a bathroom scale, just your typical scale. And imagine that I put an object on top of the scale. Okay. Gravity is going to pull this object down. But the normal force of the scale is kind of pushing back. Because the scale is preventing the object, whatever the object is, from crashing through it. And what the scale does is the scale recognizes how much normal force is needed. That's what it's calibrated to do. It recognizes how much pushback do you need in order to like balance it again, get it back to equilibrium. And that's what a scale weighs. That's what a scale measures. A scale measures a normal force, which we call a weight. However, you know what a scale really does though, is a scale then divides by 9.81. Because when you get a number off of a scale, we don't usually get a number in newtons, we get a number in kilograms. And so since this number right here is in newtons, a scale will then automatically divide by 9.81 and then tell you what your mass is. The problem is that we use those words interchangeably. So if I ask you how much do you weigh, which you probably shouldn't, that's not a polite question, but if you ask someone how much they weigh, what you're really asking is how much mass are you comprised of? That's really awkward. No wonder we don't say that. But you're really asking mass, right? And so what the scale does is it finds a weight and divides by 9.81. Did that make sense at all? Okay, so let's try this example here. What I'd like to do is try to calculate the apparent weight of a 100 kilogram astronaut who stands on a scale on Mars. Now, this is a dumb question. I mean, when is an astronaut going to stand on Mars on a scale? But it's a good thought experiment. So let me see if I can try to represent this scenario here. Now, you've got your scale, but the scale is on Mars. So, is gravity on Mars as much as it is on the Earth? Actually, I'm not really sure yet. I mean, I know the answer, but let's calculate it. Can't we find the amount of gravity on Mars? Isn't it equal to big G m over r squared? Okay, so let's calculate that real quick. That's going to be 6.67 to the minus 11 times by Mars's mass. We did the moon and we did Jupiter. We didn't do Mars, though. This was Mars, right? Yeah, this was Mars. So Mars is 642 to the 23. And then the radius and Mars is going to be 340 to the 6. I'm going to find this answer and store it in my calculator. So if anyone wants to try along, see whether you get what I get. Okay, so apparently Mars doesn't have as much gravity as Earth. I got a value of 3.70 meters per second squared. I'm going to store that as letter A. Anybody else get that value? Okay, so now let's talk about our scenario here. You're now an astronaut standing on a scale on Mars. Go with it, okay? You're going to get pulled down by gravity. Now, when you get pulled down by gravity, let's use the formula Fg, right? You're getting pulled down by gravity. Let's go mass, 110 kilograms, and let's times by gravity, which is now letter A. This would be called your weight. So if you took that value and times by 110, on Mars, you have a weight of 407 newtons. But what is the scale going to say? Now, the scale doesn't actually tell you newtons, right? The scale tells you kilograms or pounds. So you know what the scale has been calibrated to do is it's been calibrated to divide by 9.81 because it's an Earth scale, not a Mars scale. You get the point here? So therefore, if you took that number and divided by 9.81, you would end up getting 41.5, which means the scale would tell you that your mass is 41.5 kilograms. Now, is your mass actually 41.5 kilograms? No, your mass is actually 110 kilograms. But because you're not getting pulled into the scale quite so much as you normally should be, the scale is going to read things incorrectly. Sure. Okay. Because it's an Earth scale, right? An Earth scale is calibrated to divide by 9.81. Sorry, if I wasn't clear on that, I said let's make it a standard scale. You make a good point. If we were now residents of Mars, we should just change the scale so that it auto-calibrates to divide by 3.70. That makes sense? So, okay, so let's talk about this question again here. Your apparent weight would have been 407 newtons, and your apparent mass would have been 41.5 kilograms. Can I use those words properly? Your apparent weight would have been the 407 newtons, and your apparent mass would be 41.5 kilograms. But do you actually weigh 41.5 kilograms? No, you weigh 110. Just the scale doesn't recognize it properly, which is kind of a weird anomaly. You ever heard how when you go into space that you're weightless in space? Well, the reason why you're weightless in space is because although you have mass, you still have the mass that you have in your body, right? But if there's no gravitational field out in outer space, if there's really no, if Earth is too far away for you, then you're timesing your mass by like nothing, therefore you're weightless. Maybe you've heard that like you would weigh less on the moon. You would weigh less on the moon. but you'd still be 110 kilograms in this example. Okay. I want to try one more silly example. Again, these are weird scenarios, but this one's kind of interesting too. I want to now find your apparent weight as an astronaut standing on an Earth standard scale, but now what we're going to do is we're going to put you on a spaceship, and the spaceship is now leaving Mars's surface. So to kind of draw this out again here, this is like a spaceship. I'm sorry, I suck at drawing, but here's a spaceship, and the spaceship is leaving. And somewhere on the spaceship is that same scale that we talked about before. And the person is now standing on the scale. This is going to be a little different. You may even want to come up to like the front here and come take a look at the scale here. Why does the scale register anything at all? Well, as soon as I put an object on it, what ends up happening is there's more gravity, and so therefore the scale has to try to push back against it. Does that make sense? You put something on the scale tries to push back and tries to equalize itself, right? But what happens if the scale itself was moving? You might think, Chris, why would it matter? But consider this here. What if I could, on the bottom of the scale, what if I could force the bottom of the scale up a little bit more? Isn't that what's happening in this scenario right here? Isn't the thrust of this rocket pushing the rocket up? And in a way, isn't it pushing the scale up into this block a little bit? So if I could push up on the bottom of the scale a little bit, and I kind of have to keep the top steady, but if I could push the bottom of the scale up, you guys can't see this from here, but I can make the scale move, right? Like if I apply from the bottom more pressure, I can get the scale to move. I mean, there's clearly not any weight on here, but I'm just pushing the bottom in. See how I'm doing that? I don't even have my finger, I have my fingers on the sides, and I'm pushing the bottom of the scale in, and I'm making the scale move. So we're actually going to test this a little bit later if you'd like to. I'm going to ask you guys if you'd like to go in the elevator and put something on the scale like either you or a textbook. The first period class did this. It worked. If you're going up in the elevator, the scale is going to read a higher mass. And the reason why is that when you're going up, the floor is coming into you. Does that make sense? As you're going up, the floor is pushing into you. And in terms of a free body diagram, if I go back to this guy right here, gravity is pushing down, but the normal force is pushing you back up. But you have extra normal force right now. The reason why you have extra normal force is that if the object is actually accelerating upwards, we can't have these forces be the same. Right? Like if the actual rocket ship is accelerating, these two forces cannot be equal, otherwise there'd be no acceleration. Which means that the normal force is going to have to beat gravity. Now, when does normal force ever beat gravity? And normally, if normal force beats gravity, things would start floating. But it's not that it's floating, it's now that it's actually moving up in the air. So if you now have more normal force, this means that your scale thinks that you are heavier than you normally are. So long story short, go in the elevator later and take the elevator up and down. If you go on the elevator up, your weight should be slightly higher because the scale is getting forced into you, and therefore there's more pressure on the scale. When you take the elevator back down, what's really happening in that scenario is that you're kind of lifting off the top a little bit. So it'd be like if you were standing on a scale and you kind of like tried to like move yourself up a little bit, you're relieving the pressure on the scale and your weight would be just a little bit less. Does that make sense? Maybe ask me questions later if you have some. Let's try our question then. In this scenario right here, let's figure out what the weight on the scale would appear to be. So let's start with our net force picture right here. We know that the normal force of the scale is getting pushed like this. This rocket exhaust is getting pushed down, right? Because the rocket exhaust is getting pushed down, the spaceship is moving up. And therefore, whatever shelf in the spaceship my scale is on is getting pushed up. Therefore, my scale is getting pushed up. And so I have a little extra normal force that I'm normally supposed to have because the scale is getting pushed into me. So I could then say that the normal force minus the force of gravity is equal to ma. That's where I'm going to start building my formula. I know the normal force has to win in this fight compared to gravity, because if it doesn't, I'm not going to go up. Now, if I want to find the apparent weight, the way a scale works is a scale finds your weight based on the normal force. So I'm going to add Fg to both sides. So Fn will be equal to ma plus fg. Okay, let's plug in some numbers. M, we know the astronaut weighs 110. We know the astronaut as well as everything else on the ship. It's not just the astronaut, right? But everything on that ship is accelerating at 20.5 meters per second. And then I have to add the force of gravity. Hang on a sec, though. Isn't the force of gravity the same thing we just calculated in the last question? Nothing's changed other than we're now on a rocket ship, right? So if I go back to the previous question, the force of gravity that I calculated way back when was 407 newtons, right? Because way back when I found the force of gravity as my weight being 110 times 3.70. So why don't I just take a shortcut here and I'll just make this be 407. Because that's how much gravity was in the normal scenario. Can you see how this is going to make my normal force be a little higher than normal? And therefore my weight is going to be a little higher than normal as well. So if I take 110 times by 20.5 and then add 407 and do it properly, I got 2662 basically. That's in newtons. Okay. That would be your apparent weight. The only reason why it's measuring so much is that, maybe we can try this here. Let's say that I were to have the scale like this, right? And somehow, I wonder whether I could do it like that. So say that someone could somehow hold onto the scale like this. So I'm holding onto the edges there. And then if I were to ask you to press just on the bottom, can you press up underneath, right? You can't see the scale, but can you imagine that as she was pressing on the bottom, maybe I can even do it like this. As I press with my chest on it, it's making the needle go further, right? By applying more pressure from this direction, it appears as there's more weight. So anyways, that would be your apparent weight. What would the apparent mass be? How would I calculate the apparent mass? What do I got to do? Divide by 9.81, yeah. So what will the scale say when we're done? Take that number, divide by 9.81. The scale is going to say that a 110-pound person now weighs 271 kilograms. You don't actually have a mass of 271 kilograms. It's just the scale's not working the way you expect it to. So that's actually it. That's where I want to end class. What I'm going to offer to you guys then is go try it. In like small groups, if you'd like to, if you don't believe me, go into the elevator, take the scale with you. Either one of you stand on the scale or put some books on a scale, and then make the elevator go up or down. If the elevator is going up, the floor is coming into you. And as the floor comes into you, it increases the normal force. Whereas when the elevator is going back down, the floor is coming away from you, and therefore it's actually decreasing the normal force. You should actually see your mass on the scale go up or down, based on whether you're going up versus down. Anyone have any questions they want to ask right now? Okay, cool. Let me give you some last instructions, then I'm actually done. That's all I got. Here's where we're at then. I'm done teaching the lecture part of the unit. We've got a lot of work to do still, though. I don't by any means think that okay, we're ready for a unit test. We got to practice this stuff. So here's our plan. We're going to write our unit test next week, Tuesday. So not next week at all. We've got a full week and a half to practice now. So here's some tasks to work on. First one, I gave you an assignment, number 1, that you may or may not have done. You can still do it if you want. Okay. There's a second assignment that's also completely optional. You can do that if you'd like as well. At some point, I'm going to post assignment 3. That's the only one I need for sure. Okay. So when eventually I post that, probably on Monday, I'll work on it over the weekend. You guys can work on that one. There's also a lab on, lab on friction. I'd like to spend some time tomorrow working on that. We're going to do a lab on an activity on Tuesday on gravity. The reason I'm calling it an activity is that I don't have the ability to manufacture Earth and the moon and test gravity between them, right? In order for us to notice gravity, the objects have to be huge. And it's kind of boring to always use the Earth as an example. So long story short, I'm going to find a simulator on the internet, and hopefully that'll help us simulate gravity on other planets or objects. So, because like the gravity between me and the stapler, we can't notice, right? So anyways, we'll do that. And then the other thing we're going to do next week is I'm going to give you a practice quiz. So we more or less have a week and a bit to do a whole bunch of tasks and work on things. So, any questions? Okay, I'm done. You guys can go wherever you want. Here's what I'll offer then. If you want to try out the elevator, I'll leave my keys and the fob nearby. Take a scale with you and go try it. The first period class did. They said it worked. So I'll pause the video and then I'll come answer your question, okay?